Welcome to Spaceverse, your portal to cosmic adventures. Scientists have just made a game-changing discovery. They've uncovered a massive underground reservoir of liquid water on Mars. Imagine a reservoir so enormous that it could cover the entire planet with water up to 1 to 2 kilometers deep, or about a mile. This revelation answers a major question that has puzzled scientists for ages. Where did all of Mars' water go? The truth is, Mars wasn't always the dry, dusty place we see today. Billions of years ago, it had a thicker atmosphere and a warmer climate, making it a very different world where liquid water once flowed freely across its surface. So, how do we know this? Let's dive into the evidence. First, Mars is dotted with valleys and outflow channels that look strikingly similar to river valleys and deltas on Earth. These branching networks suggest that water once carved out channels and deposited sediments, painting a picture of a once water-rich planet. Next up, we have the amazing discovery of hydrated minerals. These minerals, like clays, sulfates, and specific salts, only form when water is present. Orbiters like the Mars Reconnaissance Orbiter and rovers such as Curiosity have found these telltale signs, giving us strong clues that Mars once had liquid water. These exciting finds are not just amazing facts, they're pieces of a bigger puzzle that help us understand the red planet's watery past. Finally, Martian rovers have uncovered sedimentary rock formations on Mars that bear a striking resemblance to those shaped by water on Earth. These layered rocks often display features such as cross-bedding, formed when water flows across a surface, and ripple marks made by moving water. However, between 3 to 4 billion years ago, Mars underwent a series of catastrophic changes that dramatically reshaped its history. The first major event was the collapse of its magnetic field. Unlike Earth, Mars lost its global magnetic shield relatively early. This magnetic field, generated by a dynamo effect in the planet's molten core, would have protected Mars's atmosphere from the solar winds, a continuous stream of charged particles from the Sun. As Mars' core cooled over time, the dynamo effect diminished, leading to the loss of the magnetic field. Without this protective shield, Mars' atmosphere became exposed to the relentless solar wind. Over time, this wind eroded much of the atmosphere, causing a significant drop in atmospheric pressure. As the atmosphere thinned, it became increasingly difficult for liquid water to remain on the surface. Water that was once liquid started to evaporate and drift away into space. The thinning atmosphere also weakened the greenhouse effect, leading to a sharp drop in temperatures. Mars shifted from a warm, wet environment to the cold, dry planet we see today. As temperatures fell, any remaining liquid water froze into surface ice or permafrost, buried just beneath the surface. But something didn't quite add up. Even after factoring in the water lost to space, Mars should still have had a significant amount left. The frozen water in the polar ice caps wasn't enough to account for all of it. This raised a fascinating question. Where could the rest of Mars' water be hiding? And if it's still there, could it support life? The answer came from NASA's InSight lander, a mission designed to explore Mars' interior. Unlike previous missions focused on surface exploration, InSight dug deeper, both literally and figuratively. Its goal was to study Mars' seismic activity, heat flow, and internal structure by looking beneath the crust. During its 4-year mission, InSight recorded more than 1,300 Marsquakes. These quakes, caused by meteor impacts and volcanic rumblings, created seismic waves that allowed scientists to explore the planet's interior. Hidden within those seismic signals was a surprising discovery, a massive underground reservoir of liquid water. Using a technique similar to those used on Earth to study underground structures, scientists analyzed how the seismic waves traveled through different materials. Applying a rock physics model, like those used to map Earth's aquifers, they found the best explanation was a layer of fractured igneous rock deep below Mars' surface, its cracks filled with liquid water. Imagine Mars, dusty, barren, and cold. But beneath its rugged surface, there's a hidden world, and recent discoveries are making it more mysterious than ever. It turns out that deep underground, Mars has something unexpected: water. But not just any water, liquid water trapped inside fractures and cracks of ancient igneous rocks formed from molten material that cooled and solidified long ago. You might picture this happening beneath volcanoes or after lava flows cool, and over time these rocks fracture, creating spaces for water to collect. Though igneous rocks aren't typically the most absorbent, under the right conditions, they can hold surprising amounts of water, especially if the cracks widen over millions of years. The idea of water on Mars is nothing new, but this latest discovery takes things to a whole new level. Thanks to NASA's InSight lander, which was designed to study Mars' interior, scientists used seismic data to detect this underground reservoir, buried 7 to 13 miles or 11.5 to 20 kilometers below the surface. That's far deeper than our current technology or even future astronauts can reach anytime soon. Even here on Earth, drilling to such depths is a monumental task. But despite being out of reach, the implications are huge. Finding liquid water this deep on Mars sparks an exciting question. Could it support life? Here on Earth, life has been found in some of the most extreme environments, from deep in our oceans to within ancient underground caves and mines. Microbes thrive in these hidden, harsh ecosystems where sunlight doesn't reach and temperatures fluctuate wildly. If life can survive in such conditions on Earth, it opens the door to the possibility that something similar could exist on Mars, deep underground in these watery fractures. This discovery not only adds to our understanding of the Martian water cycle, but it also reshapes our search for life. For years, scientists have been fascinated by Mars' past, when it had a thicker atmosphere and liquid water flowed across its surface. We've seen evidence of dried-up river valleys, ancient lake beds, and even minerals that only form in the presence of water. All of these clues point to a wetter Mars billions of years ago. But as time went on, Mars lost its magnetic field, and without protection from solar winds, much of its atmosphere was stripped away. The water that once flowed freely began to evaporate, and what remained froze into the ice caps or became trapped underground. And yet, even after accounting for all the water lost to space, something didn't quite add up. There should still be more water somewhere on Mars. The polar ice caps alone can't account for it all. So where did the rest of the water go? This hidden underground reservoir might just be the answer. But while we know it's there, getting to it will be another challenge entirely. Drilling through 13 miles of rock on Mars is far beyond our reach for now. However, even if we can't access it directly, this water could give us vital clues about Mars' climate history and its potential to support life. Let's not forget, this discovery was made using seismic data, the same technique we use here on Earth to map underground aquifers and oil fields. By analyzing how seismic waves travel through different materials, scientists can infer what's hiding beneath the surface. In this case, those waves pointed to fractured igneous rock filled with water, something we've never confirmed on Mars before. This underground water reservoir could even lead to new insights into how water behaves on planets with very different climates from Earth. Could there be other planets, even beyond our solar system, hiding similar underground reserves of water? And if so, could they support life too? These are the questions that keep pushing scientists to explore deeper, both on Mars and across the universe. While this discovery doesn't guarantee that life exists on Mars, it certainly makes the search more thrilling. If life ever existed on Mars, it may not have been on the surface, but rather deep underground in these hidden, watery worlds. And who knows, someday with the right technology, we might explore these depths and uncover secrets that could change our understanding of life itself. This discovery adds a fascinating chapter to Mars' story and brings us one step closer to answering that age-old question, are we alone in the universe? With the recent discovery of a vast underground water reservoir on Mars, it's tempting to imagine the red planet as a potential future home for humans. However, reaching that point remains a distant goal, and there are 5 major challenges to overcome. First and foremost is the sheer distance to Mars and the time required for the journey. Mars is about 225 million kilometers or 140 million miles from Earth on average. A round-trip mission would take roughly 18 to 30 months, which includes the time needed for travel, staying on the planet, and the return trip. Astronauts would need to bring enough supplies for the entire mission, and the distance would cause communication delays, making it difficult to provide immediate help from Earth if any problems occur. The second major obstacle is the significant threat of radiation. Space is filled with harmful cosmic rays and solar particles that can pose serious health risks to astronauts. Here on Earth, we're shielded from much of this radiation by our planet's magnetic field and atmosphere, which act as natural barriers. However, Mars does not have a protective magnetic field or thick atmosphere like Earth, leaving astronauts far more exposed. During the journey to Mars and their stay on its surface, astronauts would be subjected to heightened levels of radiation, increasing the risk of long-term health effects like cancer, radiation sickness, and damage to vital organs. Developing effective shielding technology or protective habitats will be crucial to ensuring astronauts' safety. The third challenge is Mars's extreme and unpredictable environment. The red planet's temperatures can swing dramatically, with nighttime lows dropping to a frigid -125°C, while daytime highs during the summer might only reach about 20°C. Such drastic temperature changes make it difficult to design equipment and habitats that can withstand these extremes. Furthermore, Mars is notorious for its massive dust storms, which can engulf the entire planet for weeks or even months at a time. These storms not only limit visibility, but also interfere with solar power generation, which could disrupt energy supply for critical life support systems. Additionally, the fine dust could damage sensitive equipment, clog air filters, and pose a health risk if inhaled. Overcoming these environmental hazards will require advanced engineering and innovative solutions to ensure both astronauts and their equipment remain safe and operational during long-term missions. The fourth major challenge in sending humans to Mars is creating a life support system robust enough to sustain astronauts for extended periods. Unlike Earth, Mars has a thin atmosphere composed primarily of carbon dioxide, with barely any oxygen and very little accessible water. This makes survival on Mars a complex task. To ensure astronauts can breathe, drink, and eat, highly advanced systems must be developed to generate oxygen, recycle water, and either grow or store food for the duration of the mission. Transporting enough supplies to last the entire mission would be nearly impossible due to the sheer volume and weight, so astronauts will rely heavily on technology to create life-sustaining resources on site. These systems must be not only effective but also incredibly reliable, as even a minor malfunction in oxygen production, water recycling, or food supply could have catastrophic consequences in Mars' hostile environment. Moreover, these systems must be designed to function with minimal human intervention, as the harsh conditions and remote location make quick repairs or resupply missions from Earth unfeasible. The thin Martian atmosphere, lack of liquid water, and extreme cold make it difficult to extract resources from the planet's environment. For example, extracting water from the soil or ice would require advanced filtration and extraction methods, and oxygen generation from carbon dioxide through processes like electrolysis or using local resources will need to be perfected. Furthermore, growing food on Mars poses additional hurdles, requiring the development of self-sustaining habitats with controlled environments to support plant life. Any failure in these life support systems could quickly turn deadly, so ensuring their reliability and efficiency is crucial for the success of any mission to Mars. The fifth challenge lies in safeguarding both the physical and mental health of astronauts during the journey to Mars and their time on the planet. Prolonged exposure to microgravity during the long trip can result in significant health issues, such as muscle atrophy, bone density loss, and a weakening of the cardiovascular system. These effects can make it more difficult for astronauts to perform essential tasks upon arrival. Once on Mars, they'll face an entirely new set of challenges due to the planet's reduced gravity, which is only about 38% of Earth's. The long-term effects of living and working in such low gravity are still unknown, but could potentially lead to further deterioration of bone and muscle mass, making physical health a major concern. However, the psychological toll might be just as daunting. Astronauts will be isolated from Earth, confined in close quarters for months, and separated by vast distances, with communication delays making real-time contact with loved ones impossible. This extreme isolation and the pressures of a high-stakes mission could lead to mental health challenges such as stress, anxiety, and depression. Maintaining emotional stability is just as critical to mission success as physical health, and it will require comprehensive mental health support, including innovative approaches to social interaction, entertainment, and coping strategies. Monitoring the crew's mental and emotional well-being throughout the mission will be essential, with strategies in place to address any emerging issues before they escalate into serious problems. Ensuring the overall health of astronauts is not just about surviving the trip, but thriving in a completely alien environment. The discovery of the water reservoir on Mars has given us an exciting glimpse into the planet's past, potentially providing future explorers with a crucial resource. Though tapping into this water is still a distant goal, it fuels our imagination for what lies ahead as we learn more about Mars. And that's it. Thanks for watching Spaceverse. From hidden water on Mars to the challenges of reaching the red planet, the journey has just begun. Like, subscribe, and join us next time as we explore the cosmos together. Keep looking up.